Okay. Thank you very much. Sorry for delay. I would like to thank all organizers of the workshop, especially Professor Andrew Eberhard and also Professor Alex Kruger. My talk is on constraint-based approximation with set-valued constraint. In fact, many works have been done on constraint-based approximation by many authors. Some authors are Deutsch from 1982 to 1997, has done several works on constraint-based approximation. In all works, the constraint functions are linear and infinite dimensional, one work in Hilbert spaces. Also, Seeley has done two works in 2002 and 2003 in Banach spaces with a finite number of constraints, and the constraint function are convex. Me and Giacomo have done two works in 2004 and 2005 when the constraint function are convex, but the numbers constraint are infinite. Also, in 2016, me and Giacomo has done a work on constraint-based approximation when the constraint function are non-convex, only differentiable. But this work has been done in Asplan space, in Banach spaces, which is Asplan space. Recently, me and my PhD student has done a work on constraint-based approximation when the constraint function are differentiable, but the number constraints are infinite. But in this work, the constraint function are set valued. In fact, in this work, by using generalized inert constraint qualification, we present a dual cone characterization of a constraint set S whenever the constraint function are convex with respect to upper set less order relation. And in this work, we characterize perturbation property of the best approximation. Also, we derive Lagrange multiplier characterization of constraint-based approximation under generalized inert constraint qualification. For this, we define the upper set less order relation by the following relation. We say that A is less than B if and only if this relation holds. Or equality A is a subset of B minus C. C is a closed convex and pointed cone. Also, C induces a partial order by this relation. We make the following assumption. Let X and Y be real linear space and Y be a partially ordered by a closed convex and pointed cone C in Y. Also, we assume that this C is proper, and let F from X to Y be a set-valued mapping. Also, we assume that C is pointed. We give some concept of set-valued mapping, F from X to Y. We define the domain of F by this set. Also, the graph of F is defined by this set, and the epigraph of F is defined by this set. In the case when we use the upper set-less order relation, we can define the epigraph of F by this set. Also, the set-valued mapping F is called C-convex if for all x1 and x2 in domain of F and all alpha between 0 and 1, this inclusion holds. And we say the set-valued mapping F is convex with respect to upper set-less order relation if for all x1 and x2 in domain of F and all alpha between 0 and 1, this inclusion holds. Now we give the definition of cotangent epiderivative. Let x bar and y bar be a point in graph of F. F is a set-valued mapping. The single valued mapping DE f x bar and y bar from x to y is called cotangent epiderivative of f at x bar and y bar if the following identity holds, where k of s at x is the cotangent cone of a subset S of x at a point x in S and is defined by the following set. Also, this cotangent cone can be presented by this set. In fact, if the point x bar and y bar belong to the interior of epigraph of F, then the cotangent cone of epigraph of F at x bar and y bar is equal to the whole space x cross y. And in this case, the cotangent epiderivative of F does not exist. We give an existence theorem for cotangent epiderivative in the special case whenever y is R. Suppose X is a null space and assumption 1.1 is satisfies. Let x bar and y bar belong to graph of F. Assume the functionals f1 and f2 from X to R satisfies these inclusions. Then the cotangent epiderivative of F is given by this minimum. Some properties of the cotangent epiderivative are given in the following theorem. Suppose that X and Y are null spaces and assumption 1.1 is satisfied. Let x bar and y bar belong to graph of F. If the cotangent epiderivative of F exists, then it is unique. Also, in this case, let the set-valued mapping F is convex with respect to upper set-less order relation. If the cotangent epiderivative of F exists, then it is positively homogeneous and subadditive. Also, we give another assumption. Throughout the paper, we assume that the cotangent epiderivative of F exists at each point in graph of F. Now, suppose that assumption 1.2 two holes. We define the subgradient for a set-valued mapping. A linear mapping L from X to Y is called a subgradient of the set-valued mapping F at a point X bar and Y bar in graph of F if this inequality holds. The set of all subgradients of F is called the subdifferential of F and defined by this set. Now we give a condition for which the subdifferential set-valued mapping is non-empty. If Y has the least upper bound property, that is, every non-empty subset of Y with an upper bound has a least upper bound, then the subdifferential of F is non-empty. Next result is, suppose that assumption 1.2 holds, then the subdifferential of F is a convex set. Moreover, if all subgradients are bounded, then the subdifferential is closed in the space of all linear bounded functions. We know a condition under which subdifferential is singleton. Suppose that assumption 1.2 is satisfied. If the cotangent epiderivative of F at the point X bar and Y bar is linear, then the subdifferential of F is singleton, that is equal to cotangent epiderivative of F at X bar and Y bar. We give the relationship between the above subdifferential and convex subdifferential. Suppose that assumption 1.2 holds, then every subgradient L of the set-valued mapping F satisfies the following inequality. From now on, we assume that X is Rn and Y is R, and also we replace the partial ordering induced by the closed convex and pointed cone C by the upper setless order relation, where whenever C is R plus. Now let S be the feasible set is equal to intersection of Sj. Sj is the constant set, and the mapping is the constant mapping Gj from Rn to R. R convex with respect to upper setless order relation, and we assume that the cotangent epiderivative exists for each constraint mapping at every point of its graph. In fact, each Sj is convex, and so the feasible set S is also convex. And also we denote by Ix the set of active indices and defined by this set. Also, we denote the conical hull of the cotangent epiderivatives of Gj, the constraint function, by Ce of x, and defined by this equality. In fact, the conical hull of the cotangent epiderivatives of the constraint functions are a convex cone and also has the following form. Now, for a subset E of Rn, we define negative polar cone of E by this set, and also bipolar of E is defined, and we define normal cone to a convex set E in Rn at a point X in E by this set. We have the following results for bipolar. This is well known. And also the properties of negative polar cone are given in the following lemma, and all of these are well known. Also for the cotangent cone, we have the following assertion. Also these assertions are well known. Now, let K be a non-empty closed convex set in Rn such that K intersection S is non-empty, and let S tilde defined by K intersection of S. Let T tilde belong S tilde. Then the cotangent cone of S tilde at T tilde is a subset of dual cone of conical hull of the cotangent epiderivative of the constraint function. Now we define generalized inert constraint qualification whenever the constraint function, whenever the constraint set is convex with respect to upper setless order relation. In fact, we say that generalized inert constraint qualification holds at a point X tilde if the cone of C of E at T tilde is a subset of closure convex hull of cotangent cone of S tilde at T tilde. We know the definition of a strong conical hull intersection property. A finite collection C1, C2, Cm of non-empty closed convex set which has a non-empty intersection is said to have a strong conical hull intersection property at a point X if this equality holds. This is the definition of best approximation for a set D in Rn and X in Rn and P in D. We say that P is a best approximation of T in D if this equality holds. This is the distance T from D and defined by this infimum. The set of all best approximation of T in D is given by this set. This theorem is a characterization of best approximation in Rn and is well known. Let D be a closed convex subset of Rn, and let T belong to Rn and P also belong to D. Then P is the best approximation of T in D if and only if this inequality holds. And also equivalently, we have P is the best approximation of T in D if and only if T minus P belong to dual cone D minus P. Now we give dual cone characterizations of the constraint set S. For this, let T be a point in the constraint set S and define M of T by this set. This set is a cone, but not convex. Also, this set is closed. In fact, under this lemma, we have M of tilde is equal to CE of tilde. These two sets are equal. The following theorem has a crucial role for characterizing the best approximation. In fact, this result give characterization, dual cone characterization of the constant set S. For T tilde in S tilde, we have M of T tilde is equal to dual cone S minus T tilde is equal to S tilde dual cone of S tilde minus T tilde. This is important. In fact, this result is main result. In the following example, we show that if in theorem 2.1 generalized inert constant qualification is omitted, then this theorem does not hold. Let G1 and G2 from R2 to R be defined by these relations. In fact, S1 is equal to R2, and S2 is equal to R plus cross R, and also S is equal R plus cross R. If let K is defined by R2 plus, and then S tilde is equal to R2 plus. For this set, S, the set of constant, in fact, generalized inert constant qualification does not hold. And so theorem 2.1 is not true. So we cannot omit the generalized inert constant qualification. So we give sufficient condition for which a strong chip property holds. Suppose that generalized inert constant qualification holds at a point T tilde. Then K and S has a strong chip at T tilde. In fact, this theorem, the converse of this theorem does not hold. The following example, K and S in example 2.1 satisfies a strong chip property, but generalized inert constant qualification does not hold. So the converse to theorem 2.2 is not necessarily true. We now give characterization of constant best approximation whenever the constant set is convex with respect to upper set less order relation. The first result is perturbation property. In fact, we characterize perturbation property of the best approximation. Suppose that S tilde is closed if generalized inert constant qualification holds at T tilde, then the following assertions are equivalent. K and S has a strong chip at T tilde. Then for any T in Rn, T tilde is the best approximation of T in S tilde if and only if this perturbation property holds. T minus this sum is a perturbation of T. Often for finding the best approximation of T tilde in S tilde, it is easier than to find the best approximation of a perturbation of T in a closed convex cone than S tilde. Here we define a function f from Rn to 0 plus infinity by the norm. In fact, f is the norm, and the subdifferential of norm at T tilde is a singleton point if T tilde from the point T star and is equal to closed unit ball of Rn if T tilde is if T tilde is equal to T star. Now we give Lagrange multiplier characterization of constraint best approximation whenever the constraint set S is upper setless order relation under the generalized inert constraint qualification. Suppose that S tilde is closed, and if generalized inert constraint qualification holds at T tilde, then the following assertions are equivalent. T tilde is the best approximation of T in S tilde if and only if there exists a G tilde in product of constraint mappings and there exists a lambda tilde such that self belong to this relation. In fact, these are KKT conditions. The objective function here is the function norm. And lambda j T tilde are called Lagrange multiplier here. We illustrate by the following example this theorem, theorem 3.2. Let Gj from R to R be set valued mapping and defined by this closed rays. In fact, domain of G1 is equal to domain of G2 is equal to R, and also G1 and G2 are convex with respect to upper set less order relation. Also S1 equal to this closed ray, and S2 also is equal to this closed ray, and S, the constraint set, is this closed interval, and let the closed convex cone K be this closed ray, and also S tilde is equal to this closed interval is equal to S.
Excuse me.
Sorry.
Could you please wrap it up? We have to move to the next talk.
Okay.
Thank you.
How much I have time?
Well, you have no time now.
Okay.
So if you could wrap up what you want to say.
Yes,
next,
because,
so that we can go to the next talk.
Yes, I have finished because
okay, thank you.
The example was the last, and this is the reference. Yes.
Okay, well, thank you very much for your talk. Unfortunately, we have no time for questions.